everyone, and welcome to Live from the Lab. I'm John Genke, and this is the show where we look at all different technologies that Brooker has developed to help scientists discover the world around us. Today, I am joined by Nate Henderson.
Hey, guys.
And our topic is XRD detectors in 0D, 1D, and 2D mode. So that's a lot of modes.
It is. It's probably not super clear if you're not routinely using a lot of them, but that's why we're here.
Yeah, I mean, a long time ago, right, they used film. So that was kind of 2D, and then they changed over to point detectors with computers. So the old scintillation counter.
Yep.
And that would be
would be a 0D mode.
0D mode.
Yeah.
Okay.
Yeah.
And then we kind of developed silicon sensors and such. So 1D is a detector with multiple strips.
Yep. So there would be you'd have a detector, and then all along the detector face, you would have like individual strips.
Okay.
And so I think it's interesting that you bring up the whole film concept because a lot of people are familiar with X-rays in terms of things like medical X-rays, and you would hold your arm up in front of something and you just have like this big plate behind it, or they used to use like big pieces of photographic film, right? And you really just needed to like shoot through it. But as we've gotten, over the past century, we've gotten really good at measuring tiny things. And one of the things that you need is you need to have like really good spatial resolution, which is why we talk about things like a strip detector or a pixel detector or something like that, because the actual array, whether they're like little pixels or whether they're lines in a detector, those are going to give you access to different pieces of information.
So a detector like this one, the LynxEye.
Yep.
What kind of detector is that?
So it's interesting you say 0D, 1D, and 2D, and the LynxEye can actually do all three of those.
Really?
Yeah.
But it just has strips. So how do you make a 2D pattern?
So there's a couple of different ways that you can approach 2D. So most people are probably familiar with what's referred to as gamma 2D. Geometrically, what you're looking at is like a laser beam of X-rays, like a spot of X-rays, and then off of that spot on your sample, what you see is these little rings. So they're cones, the divide cones, and then wherever your detector is, you intersect this and you get little rings. So if you've ever looked at a 2D frame or something like that, or if you think about those, like that film example, right? Some of the old camera films would have, you would see like these sort of like arcs in them, right?
Yep.
So for the LynxEye, let's see if I can do this without knocking it off the table, right? The LynxEye has strips that are oriented top to bottom like this, right?
Okay.
So one way that you could look at 2D in a traditional gamma 2D mode would be to actually rotate it, which is why we have this box here on the detector. Is it's very easy to just like rotate it 90 degrees, and then your strips are now pointed this way. So you actually have resolution in the gamma direction, right?
And then you would just put a slit in front of it to get the 2 theta and scan to build it up.
Exactly. So then your detector would be moving this way, right?
Okay.
Another way to do it would simply be to just not touch the detector at all and use what's known as a Bragg 2D. So Bragg 2D uses the same geometry that you would for a traditional powder diffraction mode, so Bragg-Montano diffraction. So that would be oriented top-bottom like this, right? So the strips are going this way, and the sample's right here, and so you're diffracting off of your sample into this, and you're just doing a traditional scan. And what this does in Bragg 2D is it allows you to collect 2D frames, so each one of these strips is at a slightly different offset, and it's going to bin all the data together and give you a related 2D frame to the traditional gamma mode.
Yeah, I think Bragg 2D is something that we're going to have a topic for a different Live from the Lab. Go a little bit more into depth.
Yeah, it's a really cool technique. We've actually got a patent pending on it right now, but it allows you to get 2D data in terms of things like sample graininess or preferred orientation, or do I have enough crystal statistics, but in the whole footprint of the sample rather than just like a little spot. So there are reasons to access both of these types of geometries, but 2D modes, a couple of different ones available with the LynxEye.
And right before we go to the video, the EIGER, on the other hand, right? Now that is a actual pixelated 2D.
Yeah, actual pixels. Yeah. So you can bend the pixels together to make strips, or you can keep them as individual pixels, or you can bend the whole thing together to make one giant 0D detector.
So this one, you can do a scanning 0D scan, so you can get your peaks. You could do a snapshot 1D, where you actually take pictures at different 1Ds, or a scanning 1D.
Yep.
Or you could do a scanning 2D to build up the 2D.
Correct.
This one, you could bin it down, do 0D mode, so you can do your scanning.
Mm-hmm.
You could do 1D snapshot, meaning you could take pictures with 1D for temperature, things like that. You could also do scanning 1D,
Right.
build up a big scan. You could do scanning 2D, where you would build up a big
Scan
2D scan,
Snapshot
or
2D.
snapshot 2D.
Yeah.
So this one adds the snapshot. And then the one other difference is what they're optimized for.
Yeah.
So this one optimized highest count rates.
Yeah.
So you never need to use a copper absorber with this. This is great for thin film.
And very large field of view.
Yep.
Which I think is
large
very
field of view.
important.
Yep.
Yeah.
So this is great for multi-purpose materials research with that high dynamic range in mind.
Mm-hmm.
Now the Lynx XCT, that's a little optimized for
Energy resolution.
Okay.
So particularly when you're dealing with things like, say, battery materials, or if you're in like an iron mine, or you've got things that tend to give you a little bit of extra background in your data, the Lynx XCT is designed to get rid of all of that and to bring your background far down.
Also, if you're doing Bragrantano and you don't want to use that nickel filter, which robs a lot of counts.
Yeah, it's about 50%.
Then XCT, that's a detector for you.
Yeah.
Now to go see this thing's actually a little bit in action, we've put together a video so that you can see what it's like to use this detector actually with different sample types. All right, so a multitude of modes.
Yeah,
Huh?
multitude modes.
So if we start with this 0D, now, back in the day, as they say, scintillation counter,
Yeah,
right?
the big old soda can thing.
That's right, soda
Yeah.
can.
Yeah.
And all kinds of fun with analog to digital and saturations and blah,
Yeah.
blah, blah.
And we had floppy disks to collect your data.
That's right. Yeah, we had to measure our floppy disks. So,
yeah.
what kind of detector was that?
It was 0D.
Okay, that was a 0D detector.
Yeah.
And is there still a use for that, or are those kind of the antiquated technology we'll never use a 0D detector?
I mean, they're still around. I mean,
Okay.
I haven't seen one in a while, but I mean, it exists. I mean, you could probably get one if you really wanted one. But I haven't seen one in a very, very long time. I haven't touched one in a very,
Is there
very
no
long time.
longer a need for 0D?
No. So it's not a matter of not needing a 0D detector. It's that particular technology has kind of been replaced by things like, the semiconductor technology. So the Lynx Eye can be operated as a 0D mode. The EIGER2 can be operated in a 0D mode. So if you need this, there's really no point in you like taking this amazing detector off and replacing it on your system with a scintillation counter and like, realigning everything and stuff like that. So it's for the 0D mode type applications, you would just switch your detector over to 0D. So these are applications like say X-ray reflectometry, grazing incidence diffraction, a lot of thin film techniques. Yeah.
Okay, so 0D, we're basically just going to bin together the channels.
The whole front of this, the whole active area of the detector is just one area. If you hit it with an X-ray, it counts.
And when I used to use a scintillation counter, I had to put a detector slit in front of it.
Right.
Do I still do that?
You can, or you can simply just use the detector active area. So one of the things we'll see when we go to lab is how you can like change the active region of the detector.
Okay.
And you simply just say, I want this to be 8 strips tall, or like, a square region with 64 pixels on either side. I mean, very, very easy to just sort of define what is your region of interest on your detector.
So I used to use a 0.2 millimeter slit. I could just type that in and it'll do it?
Just say, I want 200 microns.
Okay.
Yeah.
Okay. Now, in terms of those 0D applications, you mentioned things like the thin film stuff, high res, kind of really high intensity, but also I already have a mirror. That'll take out the K beta.
Yep.
So for that high intensity application, that EIGER is going to be the right detector, right?
Exactly. So the EIGER's, one of the hallmark features of the EIGER is what we refer to as like high dynamic range. And this is basically, if we think about it like your eyes being able to make out visible light, it would be the ability to, if you've ever gone to the eye doctor, I mean, nice glasses today, right?
Yeah.
When you get your eyes dilated, they're just like super big, and it's like you're very sensitive to light, right? There's only so much that you can take in. The EIGER is really cool because it's able to make all of these really, really high intensity things off of, say, like epitaxial thin films or X-ray reflectometry, where you're like really high counts, but you're still able, the range of that is still sensitive to the very, very low things. So if you've got a very, very thin film on top of that, and there's not a lot of material that's diffracting or contributing to your signal, you're still able to make that out because you've got the sensitivity at both high and low.
Okay, so you've got your substrate peaks, very, very high, millions of counts per second, and you got that background or the fringes that come out in XR, the same deal, very high intensity at the beginning of the scan, very low at the end. That's going to be the detector for you. Would you ever use, then, this detector for like a 0D situation?
Yeah, and I mean, I feel like, maybe we should also talk about the 1 and the 2D applications, right?
Yeah.
But the Lynx Eye, again, is going to be primarily, it has this exceptional energy resolution. So if you're dealing with something that fluoresces, so a lot of people are doing battery materials, developing new energy storage things, so iron, cobalt, nickel, manganese, all the classic problem children with copper radiation. This is just going to like the extra background off of those sample types just gets brought back down. So
okay.
Yeah.
So that's the 0D type detector if you have the fluorescence coming from the sample, some of that background. This would be the one if you need the dynamic range. Now, to go a little bit more into depth in the 1 and the 2D modes, we're actually going to touch base on that in the lab.
Yep.
So we're going to head over to the lab now and see the 1D and 2D modes, and also see what it's like to actually change these things live in action.
Yeah, sounds great.
All right,
See you
let's head
down
over
there.
to the lab. So here we are in the XRD lab, and we're going to take a look at the instrument and see how easy it is to do this 0D, 1D, 2D switching.
Yeah, sounds great.
All right, so how's the instrument set up right now, Nate?
So the system right now is set up for a powder diffraction scan, a traditional 1D scan. Well, why don't we open the doors and I'll give you a little look inside. So this is a copper sealed tube.
Okay.
So last month we talked a little bit about X-ray sources. So
Yep.
This is the sealed tube. It is set up with a line focus, which means it's going to be shooting a line of X-rays down onto your sample.
Okay.
Okay.
So big, broad line beam.
Big broad line
Yep.
beam to match the size of your sample surface.
Okay.
Now, right here, combination optic. This is called our trio. The trio optic has 3 different beam paths associated with it, all software selectable. The one for most commonly going to be the diverging beam. So this is a motorized slit. It can be a very big slit. It can be a very small slit. Whatever's most appropriate for your sample. But this is going to give you a Bragg-Brentano beam, which is going to diverge as a line down into your sample, and then focus back onto your detector after it diffracts off your sample.
Okay. And what's that little slit right after?
This one right here is a nickel filter.
Okay.
So this is going to filter out K beta, and this is going to filter out some of the white radiation as well.
Okay. Now on the detector side, what do we got going on?
Okay. So on the detector side, you can see that this detector is pretty tall, right? So that's one of the nice things about this detector is that it's got this aspect ratio. We'll be using this a little bit later when we get to 2D. But right here, this is an axial solar. So this is going to collimate the beam in this direction. So this is going to control any sort of axial divergence. And then what we're going to do is we're going to be able to use the whole of this detector. So right now, this is set at a very big 2 theta coverage, right? Which means that I'm able to collect at this distance about 14 or 15 degrees of data at one time.
Oh, wow. Just in a snapshot.
In a single snapshot, right? But we're actually going to use this in a scanning mode, which is going to move the detector up. It's going to move the source up. Traditional Bragg-Brentano scans.
All right, let's head on over to the computer and see that in action.
Okay. All right, so on the software, I'm going to go ahead and start the scan. I've got some settings already programmed in. You can see on the left-hand side that I've got a lot of drives on this particular system. This is set up with a cradle.
Okay.
The cradle allows me to control psi and phi, so these are going to be tilt and rotation. I also have the ability to do X, Y, Z motion, so this is going to be for any sort of large parts, or if you have to maneuver a piece into the center of the instrument. This is set up right now with the motorized slit. Okay, you can see it's already starting to collect data. So this is the motorized slit. This is going to be a 1 millimeter divergent slit, which is then going to diverge onto your sample. 1D mode on the detector here. So this whole 1D mode right here for the detector drop down is going to be something we'll use here in a little bit when we switch back and forth between 0D and 1D and 2D detectors. Otherwise, you just simply need in your scan parameters. We're doing about a minute of data collection, so really, really fast data collection. You can see already as the data that's coming in, this is really good signal to noise, really good signal to background.
So this would be great if you're doing like qualitative phase ID or quantitative refinements.
Yeah, so this is a mineral specimen.
Okay.
This is actually calcite.
All right.
So we see that in the span of a minute, I'm able to get 6, 7, 8 different diffraction peaks, which is enough to do a fingerprint ID. And then to do some sort of like quantification, we would look at peak intensities.
So then to increase the confidence we have in that end result, though, it might be nice to know if we have any preferred orientation issues or if we had any crystallite size issues, like that really big tall peak there. Is that actually supposed to be big, or is it?
Yeah, I mean, and particularly with carbonate minerals, this particular reflection can sometimes be enhanced because the mineral likes to, it has a cleavage direction. If you press down too hard on it, you can orient it.
Yeah.
So we would be looking at something like, say, preferred orientation or texture, depending on how you're defining that. So let's actually take a 2D scan of this real quick, just to show you what that would look like. So we'll go back over to the instrument real quick.
Okay.
A couple of hardware changes very, very quickly that we'll do. The first thing I'll do is I'll put in a pinhole collimator. So this is just a little hole. Okay. I'm going to be using the That's a very nice straight parallel beam. I'm going to use one pinhole here, and then a collimator, which is going to give me another pinhole very close to my sample. These are magnetically attached, so it's on. No wrenches, no screwdrivers or anything necessary. The magnets just attach it in at the same position every time. So now I've got this straight parallel beam and two spots, two holes that are going to generate a very, very straight point on my sample.
Okay. Yeah, and that's important for getting those nice sharp Debye rings.
Exactly. So I'm going to have a 1 millimeter spot here, 1 millimeter spot here, which means on my sample it'll be about 1 millimeter.
Okay. So what do we got to do here on the detector?
Okay. So on the detector side, what I'm going to do is I'm going to take off this axial solar. Okay. I don't need that in 2D mode. And you can see right now my detector is oriented as a taller direction. So this is a 2 theta direction. What I want to do is I want to rotate this to give me more coverage in the gamma direction. Okay. So the easy way to do this, I'm going to put a little shield in there.
Okay.
Just to keep me from touching it with my fingers. All right. There's a handle which goes on to the top. Very nice. Easy way to do that. There's a switch in the back which releases the detector. I'm going to rotate it. Okay. And then lock this back on.
Okay. And when you turned it, there's actually like a magnet that helps to pull it into the right spot, right?
Yeah, exactly. Yep. And there's also all these little chips on the detector, which means the system will automatically recognize which orientation it's in. So I'll take the shield off, and you can see now that we've got a wider detector. So this is going to cover more in the gamma direction, right? Which is going to give us more of those Debye rings, more coverage of those Debye rings.
Okay. And if you had that new 250K version of this, it's a square sensor.
It would be a square.
So you don't necessarily have to turn it.
You would never need to turn it. But for the 500, we're going to go ahead and take advantage of that extra coverage.
Okay.
Yep. All right. So then if we go back over to the software, I'm going to switch to that global mirror. Remember, I want to use that nice parallel beam with the pinholes. And then on the detector, I'm going to go to 2D mode. Easy enough, drop down. There's no fiddling around with it. If I look at my detector view, this is a really neat little utility. And what it allows you to do is change the size and shape of your detector. So if I wanted to do, say, the 250, it would be a square. For the 500, I can use the full active area. So we hit OK. Apply.
And there, I could also see those energy settings, so you can even have thresholds to give you better background.
So if you had something like, say, some iron in your sample, that would give you a little bit of extra background. You can play around with those settings to reject out a sample X-ray rather than a diffracted X-ray.
Okay.
So we're just going to go ahead and I'm going to run the same scan that we did before.
So you don't have to change the settings because it's a 2D?
No. I mean, I just need to change it to 2D mode, and then take off that axial solar. But this will automatically update. It's not a different software. It's not a different software mode. It's all integrated into the same settings. Of course, you could change your 2 theta starting and stopping values from wherever you want it to be. But once all of my drives are initialized, it'll be ready to go. So once this starts collecting data, what we'll see is that switch over to a 2D frame. So rather than have that traditional 1D scan, on our screen, what we can see is that the Debye rings will start to come in as we're scanning through.
Okay. Yeah, I'm starting to see some data now. It actually almost looks like that panoramic mode on my camera.
Yeah. So if you've ever taken those like very wide horizon shots or a skyline shot, you sort of move the phone or move the camera through that. And what's really cool about this is this scanning 2D mode is something that took a lot of development time to really get it properly integrated into the system. The old school way of doing things would be you would take a couple of frames and you would kind of like
take a picture,
tape another picture, tape another picture, almost like a jigsaw puzzle. And this allows you to sweep through the entirety of your 2 theta scanning range as a single frame.
So every pixel is kind of covering every one of these rows.
Yep. So you're taking it's a lot of data, right?
Yeah, that is.
So what we can see here is that if there's any sort of graininess or spottiness, maybe your sample isn't ground up very well.
Yeah.
Or if there's streakiness, maybe this is a texture.
Okay. Yep. So on that second peak, the really bright one, I'm not seeing either of those effects. So it looks like it
looks like this is probably a pretty well prepared powder.
Okay. So now, if I wanted to do something a little more complex, I mean, here we did some simple scans, but what if I wanted to do like a pole figure for texture analysis?
Okay, perfect. So we were talking about what if one of your rings is streaky? What if there is some sort of texturing or preferred orientation?
Yeah, I had a chunk of metal or something with a lot of texture.
And so the way that you would measure this is you would use this cradle to tilt, and rotate your sample. And you're actually going to collect the Debye rings as a function of the entire.
Okay. So do I have to go in and manually just collect all those pictures? Oh, wait. Okay. Yeah. Looks like we've got a little.
We've actually got a little plan here. So let me show you what it would look like under a traditional point measurement.
Okay.
So if you had, say, a scintillation counter. What we see here on the screen is all of this is going to be a function of rotation and tilting of the sample. And we're going to point the sample at different directions. And every one of these data points would need to be filled in. So you would need to take a data point at each one of these spots.
Yeah, I don't think that's going to make a very good pull figure.
We're missing a lot of data points in through here.
Yep.
With the 2D mode, each one of these lines represents the coverage that you're getting with a very wide gamma slice.
So that's kind of covering the whole length of that line that we saw in the 2D.
Exactly. So it's a very quick way to get a lot of data very, very fast. And to give you a frame of, a sense as to how fast it is, this whole thing takes 12 minutes. That's not 12 minutes per frame. That's 12 minutes for the entire pull figure.
Yeah, and one of the other nice things is that you actually get a decent 2 theta coverage, so you might actually collect 2, 3 pull figures all at once.
At the same time.
Yeah.
Right. So if they're close enough together, you might be able to only measure one thing and get a complete ODF because you've got 2 or 3 reflections in the same.
And there's wizards like this to support if you're doing a 0D, 1D, or 2D modes,
exactly.
right?
So Wizard is great for stress. It's great for texture. If you're doing non-ambient diffraction, there are planning tools in for that. Any sort of RSMs or high-res work, if you're looking at, say, like epitaxial thin films. All of these different planning tools are really useful in terms of setting up your experiment and kind of guide you to taking all these complex sets of data, but really wrapping your brain around where your sample is and what you're analyzing.
All right, so it looks like we got a pretty good overview here of 0D, 1D, and 2D, what it takes to change between them and how it's integrated into the software. We're going to head back over to the studio and answer some of your questions that have come in live.
All right, we'll see you there.
All right, so here we are back from the lab, and we have a few questions that have come in. But if you do have any additional questions, type them in the live chat or email them to live.events@brooker.com, and we'll get back to you on those questions. So the first question comes from Prabir, and the question is, what is the maximum capture angle of the EIGER2 R 500K detector in snapshot 2D mode?
It's a mouthful.
Yes.
What is the maximum capture angle? Okay, so there's a couple of ways that you could think about this, right? So if we look at the EIGER and we're talking about like the sort of like the active area here, the maximum capture angle is going to depend on what direction you're defining. So is it in the 2 theta direction or is it in gamma? As well as how close is your detector to your sample.
Okay.
The closer you are to your sample, the bigger that angle looks. The further away you are, the tighter your achievable resolution. So at a sort of a normal distance of, say, 280 or 300 millimeters, in the 2 theta optimized mode, you're probably looking at about 14 to 15 degrees of coverage, which is, if you think about it, quite significant. 14 to 15 degrees will give you, a couple of peaks to work with if you're doing, say, like a snapshot, 1D mode or something like that. If you're using an application where you wanted to get more coverage, you could just simply move that detector in towards the sample and get a little more.
I use it a lot at 10 centimeters. So 100
really
millimeters.
close,
And there we're talking 40 degrees of coverage when you're in that max mode like this.
Oh, you're talking about gamma?
In the 2 theta mode. So I guess it would be
so,
like
so
this.
2 theta.
Yep.
Okay. Yeah.
Yep. So when we're at 100 or 10 centimeters, we get about 40 degrees of coverage. And then if you go even closer, I think the maximum I've done has been something on that order of 5 centimeters, a little less.
Uncomfortably close.
Yeah, uncomfortably close. And there we're sitting at almost 100 degrees.
Yeah.
So,
I mean, it's also, I think it's relevant to point out, it's not just 2 theta coverage, it's also, if you're looking at, say, like the 2D mode, it's also gamma.
Yep.
Because for things like stress and texture, if you get your detector really close to your sample, I mean, number one, don't touch your sample, but you're able to get more of those Debye rings.
Yep.
And so if you were looking at either elongation or compression of the ring for 2D stress, or if you were looking at any sort of streakiness for things like texture, you just get more data. There's more to work with.
Yeah, yeah. So next question is from Erikita, and that question is, does the use of 0D, 1D, and 2D also condition the use of the divergence slits?
Does it also condition the use?
So I think it's...
Like, does it require the use of that?
Yeah.
Okay, yeah, sure. We'll go with that. The use of divergence slits, okay, so in say, a 1D mode, a traditional 1D mode, we think about this inherently using things like a divergence slit. And that divergence slit is going to define the size of your beam in a line focus and then diverge into your sample and then refocus towards your detector. For Bragg 2D, which of course, we may be looking at that in a future episode, right? You would use the same geometry. So divergence slit, sample, back. In Gamma 2D, you're going to actually take some sort of collimation because Gamma 2D requires you to have a spot. So a little spot that goes down into your sample and then diffracts off in a cone. So you could use divergent slits. I generally don't think about them in terms of like a divergent slit because when we were down in lab, we were using a mirror, which gives you a very straight beam. But then we had 2 pinhole collimators that were of a fixed size. So they will control things like spread and divergence, but they're not really a divergent slit. Yeah, I guess it's sort of a it's a weird nomenclature thing, but yeah. So in general, anytime you're looking at slits, a bigger slit gives you more intensity because you have more X-rays. A smaller slit will give you a tighter achievable peak by reducing your instrument.
So maybe let's talk about maybe the 70% of scenarios. The most common scenario would be 0D mode. You're probably going to use some sort of a parallel beam that's generated either with a mirror and a slit. So you're going to come in at that very narrow angle. But you could also just use this very small divergent slit, ideally 2 slits lined up. That's going to give you kind of a pseudo-parallel beam. So 0D mode. 1D mode, like Nate had said, you're going to use a divergent slit in the classic sense. You could also use a parallel beam with a tiny slit. We've done that before.
We've done that.
And then 2D mode, you're going to make some sort of spot. Yeah. So you could have a tube that's turned to point focus, followed by another pinhole. You could have 2 pinholes. For that Gamma 2D, where you're doing kind of side 2D method with the rings, there you're looking at a point. Or you could use Bragg 2D, and that's going to use the fully divergent beam and 1D mode to make a 2D image.
It looks like we have a question about the tube. Okay, so was the X-ray tube in line or point mode during the 2D scan, and was the data collected with the same setup we've just? Okay. So the X-ray. So this is kind of an interesting question because like we get this. I don't want to say confused, but often it's not as clearly delineated as it should be. You have the X-ray tube, which has different focuses. Right. You can either do a line focus on the X-ray tube, where you're generating a line of X-rays. You can do a point focus, where you're generating along the focus, along the filament, down to your sample. So coming out of your tube itself, having a point, so line or point. And then you also have the collimation or divergence in terms of the optics right in front of, or I guess right after the X-ray tube, right? So if you were using a line focus and a mirror sheet of X-rays, a very straight parallel sheet of X-rays, you can create a point focus, a spot beam, using a line focus X-ray tube. To answer your question, the X-ray tube was in line focus. We were using a mirror to create a flat sheet, a parallel sheet of X-rays, and then 2 pinholes in front of that to make a 1 millimeter spot down onto the sample. And then the pull figure, which we saw in kind of the pre-movie, that one was collected, exact same setup. So we used the trio on the primary side with the mirror, 2 pinholes, and then we hit it. So thanks, Giacomo, for that question. Next question from Jan. You started your scan at 20 degrees. Is there a problem with the EIGER detector below 20 degrees? Oh,
We're trying to use movie magic here to cover up some dirty secret, Nate.
No, we were trying to like do a 50-second data collection, and that's calcite. And I know that inorganic materials, there's not really anything going on at low angles typically for carbonates or oxides. If I were looking to say like a clay mineral, I would obviously want to go much lower. But no, there's no problem with the EIGER. If you go down to lower angles, you can use a smaller divergence slit. You can close down like we saw with that that dynamic detector opening thing. You can change the size of your detector to match your starting angle. Obviously, with a very large field of view, one of the things that you want to think about is as you're at lower and lower starting angles, making sure you're not like shining the X-ray directly into the detector, because it gives you extra signal.
Yeah, it's not going to hurt the detector.
Yeah.
The issue at the low angle, say with the EIGER detector, is just background.
Yeah.
So, and if those photons are not going to give you a signal, they're going to give you a background. In fact, this is a great detector for SAX analysis. We're going to shoot at low angle. You can shoot the direct beam into it, no problem there.
Really good at X-ray reflectometry too, because we talked about that whole dynamic range thing, where you're able to get like the higher end and the lower end, all in this without any sort of absorbers or anything like that, and all of that is done at very, very low angles, like half a degree.
Yep.
So no, it's a great detector. We just, that particular sample didn't need it. So.
Yeah. One other thing to note, you did notice that we used air scatter shield over the sample. And
little blade thing.
Whenever you do low angle measurements, you're using a 1D detector, 2D detector, whatever mode, having that blade over the sample is absolutely essential to achieving great results at low angle.
Yeah.
So we have come to the end of our time. If we haven't gotten to your question, or if you have any additional questions, please make sure you email those to live.events@brooker.com. And until next time, keep your signal high and your background low.